Welcome to Chapter 23, Electromagnetic Induction, AC Circuits, and Electrical Technologies. Be sure to pick up the PDF off of Canvas. This one will be 23.1 so that you can follow along. Remember in the previous chapter, we talked about forces on charged particles moving in a magnetic field. So for example, if I have a uniform magnetic field and I put a charged particle with a velocity v that is perpendicular to the magnetic field, it will exhibit uniform circular motion because the force on that charged particle is QVB sine theta, where v and b are perpendicular to each other and F is perpendicular to both those vectors. Now, if I restrict the motion of that charged particle by placing it inside of a wire, then the negative charge particle, moving with a velocity v to the right, which is equivalent to a current, positive current flowing to the left, again, the charged particle will feel a force, which will cause it to move down, but it's restricted to stay inside of the wire. And so that force will be exerted on the wire, and the force on the wire is ILB sine theta. Now, we can use that to cause the wire to move. And so next we talked about taking a loop of wire, putting it inside a magnetic field, and then running a current through it. So if I run a current I through this wire, you can go through the right-hand rule and figure out what the direction of the forces are on these segments. What you'll find out is that this wire, if I put it on an axis, will want to rotate about that axis. This is the beginnings of building a motor. In the case of a motor, we are taking electrical energy and turning it into mechanical energy. Electrical energy causes currents to flow through the wire, exerting forces which make them rotate inside of the magnetic field. Now in this chapter, in chapter 23, we want to reverse the process where we take mechanical energy and turn it into electrical energy. So if I take this situation where I have a battery and I have the wires connected to the battery and they're coiled around an iron ring like a washer, when I close the circuit, when I close this switch, current will flow through this wire. In addition to that, I will notice that this galvanometer will register a signal. The needle will swing either left or right. And so what's happening is the current is flowing through the wire that's connected to the battery. That's creating a magnetic field. That magnetic field will, for the most part, stay inside of this iron ring. And so the magnetic field passes through the loops of wire on the bottom part of this iron ring, which is attached to my galvanometer, and the galvanometer will register a signal when I close the switch and when I open the switch. There are a few things to notice about this, though, is that the direction changes. So sometimes the needle swings left, sometimes the needle swings right, and while the switch is open or while the switch is closed, the needle reads 0, meaning there's no current flowing in this secondary loop. It only moves when a change occurs, when the switch opens or when the switch closes. We can illustrate that with this picture down here. Figure 23.4 from your textbook shows a series of steps where we're taking a bar magnet. We've got a coil of wire attached to a galvanometer, and we're going to take that bar magnet and move it toward the coil and away from the coil. First with the north pole of the bar magnet, and then with the south pole of the bar magnet. And if we pay attention to the direction the needle swings, we can figure out which way current is flowing through this loop. And what we'll notice is when we move the bar magnet in one direction, in particular up, current flows in this orientation. If we move the bar magnet down, current flows in the opposite rotation. If I flip the bar magnet and then use the south pole, I get the opposite effect. When I move the bar magnet up, the current goes opposite the direction when I was using the north pole moving up. And when I take the south pole and move it down away from the loop, again, I get the opposite direction of current when I did the same operation only with the north pole. And also, no matter where the bar magnet sits, when it's stationary, there's no signal. There's no movement of the needle. Now, it's not really feasible to generate electricity by waving a bar magnet back and forth near a coil of wire. Usually our mechanical system is best suited for causing something to rotate. And so if we have our mechanical system make something rotate and we attach that to a coil of wire inside a magnetic field, then we see that connecting this wire to a galvanometer. While this is rotating, we see current flowing as evidenced by the galvanometer needle swinging back and forth. Again, we note that as this rotates, the galvanometer swings first one way and then the other way, which indicates that current is flowing first one direction and then the opposite direction. In the next chapter, we're going to quantify this property. We're going to introduce Faraday's law and Lenz's law. But before we do that, we need to define a term. And that term is magnetic flux. Magnetic flux, which we give the symbol Greek letter phi, is the idea of magnetic field moving through a surface. It's defined as B times A times cosine theta. Theta is the angle between B and A. It's not obvious what the direction of an area is, but we define the direction of the area as the perpendicular to the area. So I have a plane here, a little rectangle, and the perpendicular to that rectangle is what we define as the direction of the area. So then we can talk about B times A times cosine theta, where theta is the angle between B and the normal to A. That's shown in the picture here. Now, flux has units of Tesla times meters squared. And again, it's the idea of the magnetic field moving through this cross-sectional area. So if we have B at an angle here, we can imagine breaking that B up into two components. One component that is perpendicular to the area and one component that is parallel to the area. And so B cosine theta, we could also look at this as the magnetic field component that's perpendicular to the area. The one that's parallel to the area does not contribute to the flux because it's not going through the area, but the perpendicular magnetic field does go through the area. Now let's calculate flux in a couple of situations. Let's say we have a uniform magnetic field of 500 millitesla. We have a square loop of wire inside a magnetic field that has dimensions of 8 centimeters by 10 centimeters. This is a top-down view, and we're going to look at a few different situations. In one case, the orientation of the loop is such that the normal is along the direction of the B field. So in that case, remember flux, B times A times cosine theta. So when the area or the loop is oriented such that the magnetic field points directly through the area, the magnetic field and the normal to the area are both in the same direction, and so theta is 0. In that case, the flux is just going to be B times A times the cosine of 0, which is 1, and so this gives me 0.004 Tesla meters squared. If we orient this, or if we rotate this slightly so that now the normal makes a 5-degree angle with the magnetic field, the flux in this case is B times A times cosine of 5 degrees. And that gives me a value of 0.00395. three significant figures. Now let's look at two more situations. When the loop of wire is oriented so that the normal is perpendicular to the B field, in that case the flux is BA cosine theta. So again, B is 0.5, A is 0.008, cosine of 90 is 0, and so the flux is 0. Which makes sense because if the loop is oriented like this, there is no magnetic field passing through the loop. It's running parallel to the loop, but there's no flux. There's no flow of B field through the loop. Now if I rotate this just a little bit by 5 degrees, so that the normal is at 85 degrees with respect to the magnetic field, then again, BA cosine theta is going to be 0.5, an area of 0.008 square meters, cosine of 85 degrees, and that gives me a flux of 0.0872 Tesla meters squared. And that's how we calculate flux. Now, one other thing I want to point out before we leave this is look at the difference between these two. In both cases, I changed by 5 degrees. So I went from 0 degrees to 5 degrees. And in this one, I went from 90 to 85. So both of them are changing by 5 degrees. The change in flux in this case is the difference between these two, which is a difference of 5 times 10 to the minus 4 Tesla meters squared. In this case, the same change of 5 degrees, but at a different orientation, is 8.72 times 10 to the minus 2 Tesla meters squared. So notice that first of all, it's not uniform, which is something we would expect because it's a cosine function, which is nonlinear. But notice that when the flux is near its maximum value, this is its maximum value. I have the most flux here. If you calculate this for any angle, this 0.004 is the largest number you'll see for flux in this particular problem. Any other angle gives you something less than this number. But when I'm at the maximum or close to the maximum flux, I get very small changes. But when I'm at or close to zero flux, I get very large changes for the same amount of rotation. We'll come back to this idea in a later section.